Right, looks like I'm live. This is going to be a Chemistry 108 lecture. I'm looking for a link now to provide the class in Discord. For those of you guys catching this after the stream, remember I will be linking in the comments the timestamp for when the actual video starts. And I am seeing the stream live, so I'm going to find a link. Where I will be linking in the comments the timestamp. Alright, and here we go, Discord. We are now live. Alright, give it a few minutes. I guess this will be a good time to let Tristan mess around on the camera for a little bit, like I told him he could. Hi!
Hi!
You say hi, look at the camera to talk, right there. That's where you look. Look right there. How about you just do the dance? How about you just do the dance? What kind of dance is that?
I don't know, but it's a dance. It's a Fortnite dance.
What kind of dance is that?
I don't know what it's called, but it's a dance.
Let's see it. What is that?
That's not what I'm doing!
Is that the dance?
Wow! That looks like nothing like me.
This is how every chemistry video should start, right? People dancing. I guess this is the good thing coming out of this. We can all dance during chemistry lectures, right? You know the floss again?
Mm-hmm.
That's easy. All right. I think whoever's going to log in is in. All right, guys. I'm sure you guys can all see me right now. So yeah, chapter 9. We're going to continue. Like usual, we're gonna wait a minute before we actually get started. Let me jump to the general chat here. Yep. All right. I'm in the Discord. All right, so it seems to be best if you want to comment during the video, that you go ahead and talk in the chat over here somewhere, and then I'll see it during the stream if you don't want to talk with the mic.
On the tablet?
So let me just make sure that he is all set up, and then he promised to let me teach again, as long as I let him dance. That's like going to be the cost, that we got to do a little dance off every lecture. You got the tablet? Cover your mouth when you talk, buddy. Where are you going to hang out at? Hey.
What?
Where are you going to hang out at?
Upstairs.
Upstairs? You have your headphones up there?
Oh, yeah?
All right. Here, I want a bro fist before you go. Bro fist. Boom! All right. All right, guys. I'm gonna go ahead and get my little setup here ready to go, and I'm gonna go ahead and start lecturing. So, I'm gonna have the PowerPoint, the activity worksheet, and then working on paper like usual. This will be the whiteboard, you know, if we're in class. All right. Let me go ahead and officially start. So, yep, today's Chemistry 108 lecture is going to go ahead and continue in Chapter 9. We are going to go ahead and wrap up the acid-base and equilibria discussion today. So it's going to be more practice with acid-base. I had a little bit more to talk about with the pH and pKa thing that we did last time. And then we also need to go over LeChatlier's principle. So we'll go through all that today. So let's go ahead and switch over to the PowerPoint. So I upgraded my setup here a little bit, so we do have a kind of a nicer display, a little animation in the background there, getting all fancy. But let me hide. What? I'm already messing up here. All right. Not showing. Let me hang on. Technical difficulty. Oh, there we go. And then I will go ahead and put it like this. There we go. All right, so last time we went over chemical equilibria. We have, seen in class how to write the K expressions. Remember, they are the products over the reactants. I didn't mention, though, in all of our reactions have been 1-to-1, but it turns out you also raise them to their stoichiometric coefficients, to that power, if they're in there. Maybe we'll see one like that today, where you have to do that. Before I get into the different examples, I did want to mention this slide here that I kind of skipped over. This slide is talking about antacids. So as you guys well know, that antacids are typically used to treat things like heartburn. Typically heartburn symptoms, excuse me, heartburn symptoms are typically caused by having excess stomach acid. And if you think about it, we have an acid in our stomach. You can neutralize it with a base. Different bases are used. Some common ones are aluminum hydroxide, magnesium hydroxide, and some carbonates are used also. There are some problems, however, if you use bases that are not hydroxides. For example, if you use carbonates, you typically will generate a lot of carbon dioxide gas, cause you a lot of belching, basically. You're generating a lot of gas in your stomach. One thing they do, if there is a carbonate base inside of an antacid, they will typically add what's called a anti-frothing agent. So that keeps your stomach acids from frothing up and coming back up, essentially, if you're generating a bunch of gas. So you kind of add things to help with that. Another bad thing, too, about antacids is if you use sodium bicarbonate baking soda, the big problem here that it can affect your level, your acid level of the blood. But the main thing that I'm concerned with using sodium bicarbonate as an antacid is the amount of sodium you're intaking. So sodium intake is significant. You're getting 1 mole of sodium ion per 1 mole of sodium bicarbonate. They are 1-to-1 in that reaction. And you're going to get a lot of sodium in your intake then, which can be bad if you have things like high blood pressure. So you don't want to have a lot of sodium in your diet if you can avoid it. Interestingly, though, we actually do a lab in Chemistry 122 where we have all the students take baking soda, sodium bicarbonate, and then compare how strong that is as an antacid to your commercial antacids like Tums and Rolaids. And we find out in the lab that per gram, the sodium bicarbonate is way better, like almost twice as better. But remember I mentioned the issues we have here. You don't have any anti-frothing agents. You also have all the sodium. And if you're not sure if you've ever tried it, but taking straight sodium bicarbonate is awful to taste. It's very bad to taste. So yeah, if you ever brush your teeth with baking soda, you know what I'm talking about here. So yeah, it's a pretty bad taste. It's really bland and not very appetizing. So usually they'll also add flavors to antacids too to make them a little bit more palatable. All right, so here I was, excuse me, here I was talking about going back to the chemical equilibria thing. If there are coefficients in there, you typically add them in as exponents in your K expression. And we'll definitely see some K expressions here today. All right, we did go over if the K is greater than 1 or less than 1, which side dominates. We did that last time. I want to go ahead and just talk about LeChatlier's principle, and then we can go ahead and jump over and do some practice problems from the worksheet. All right, so one of the common examples or comparisons I was making with the chemical equilibria is that we have a scale. So imagine you have a scale like one side's product, one side's reactants, and it turns out if you actually disturb the scale in any way, the scale kind of adjusts accordingly. And I actually have a meme here that I wanted to show you guys that goes along with this. Let me load the meme. So pictures, desktops, memes. Yes, I made a memes folder for online teaching. Is it showing? Hang on. Yep, there it's showing. You guys should be seeing it on the upper right of the screen right now. And I thought this one was pretty funny. So it says there, if a stress is applied to a system in dynamic equilibrium, the system will adjust to relieve the stress. That's basically what's happening here. So the scale will realign and rebalance to make sure that K value stays constant. So here we see a guy with a bunch of paperwork, it's piling up, and then he equilibrates by just burning it all. So if you're working from home, don't do that with your paperwork. You might get in trouble from your boss. So yeah, I thought it was a really appropriate meme for what's going on right now, as well as the concepts for today's lecture. And let me turn that off. Boop. Yay, getting better at this. All right, so let's go back to the PowerPoint. So the way we basically take a look at LeChatlier's principle with a chemical equilibrium is that if you make one side heavy, the reaction will adjust and proceed more towards the other way to get the reaction to kind of balance out. So I'm looking here, let me bring up that, there we go. So I'm looking right here where we have this reaction. This is called the Auber process. This was discovered during World War I as they're trying to figure out how to make nitroglycerin, but they figured out how to make ammonia, which is used in agriculture. Anyway, we do have a chemical equilibria here. In this case, if we add more nitrogen into the system after it's already equilibria, the equilibrium will adjust to shift to the right. So we're making the reactant side heavy. It's going to generate more products to kind of equilibrate. The reverse case here is if you take some of the reactant away, it'll actually shift towards reactants to compensate for the imbalance there. It should be pointing this way. Yeah, so if we remove H2, it'll shift towards the left. If we add anything, it'll shift towards the right, like that. Ooh, that's all backwards from my actual perspective. So, all right, so this definitely has a play on temperature as well. Recall back when we did energy of reactions, I showed you guys back then that if you have heat involved in a reaction, we can add them in as a product or a reactant. So in the case where a reaction is exothermic or exergonic, I think is what the word we're using, your reaction is releasing heat. So you can think of heat over there on the product side as a product. So what will happen here is that suppose that you were to heat this reaction up, you have an exothermic reaction that's giving off heat, you're basically adding heavy to the product side. So what ends up happening is it shifts to the left. Yeah, that way. And then if you were to take away heat, basically you cooled it off, you're taking away from the product side, it shifts towards that way to make that way to make up for the loss there. Maybe I should stop pointing. I'm pointing in the wrong directions. But you guys see the reaction on the screen right now. So once again, if you have an exothermic reaction, adding heat will shift towards reactants, and then cooling it off will shift towards products. It is literally the exact opposite if you are dealing with an endothermic or an endothermic equation. You have the heat on the reactant side, then everything is flipped then. This slide here has a summary. I don't recommend really memorizing it by like what can happen. I prefer if you logic your way through it. So you can use this to help you out, but I recommend you learn the logic, and that way you can answer any question and not have to refer to this slide. So, and the logic isn't too bad, so it should be okay. All right, I want to go ahead and take a look at an acid-base reaction and how we can kind of use writing out some reactions here, and then we also need to get some practice in predicting equilibrium shifts. So let's go ahead and start with the reaction. We did go over strong acids, strong bases, weak bases last time a little bit, so I will go ahead and continue with that here. So switching over to presenter camera. All right, so I want to go ahead and start with the weak acid. So a weak acid would be something like, I think we used vinegar last time. Let me do a different one here. Let's do formic acid. Formic acid has this formula. I want you guys to know the shorthand like this as well as if you actually write it out, like drawing the structures out. I'm going to do that also in this problem. So this is going to go ahead and serve as a weak acid. And then we're going to go ahead and react with, let's say, potassium hydroxide. Hydroxides are strong bases. So strong base. And we're going to go ahead and use an equilibrium arrow here, but it might be one-sided because typically if you have a strong base or acid on one side, the reaction usually ends up being one-sided. If they're both weak, you typically have a proper equilibrium going on. So what's happening here is we have a K plus and a HCOO minus. So remember, we lost an H here. So your acid is going to lose an H, and your base is going to gain an H. So your base is going to become H and OH, which is water. I did want you guys to recognize conjugate pairs that we take a look at. So what you want to do here is you take a look at what the acid became. Remember, acids are going to basically lose an H. Bases are going to gain an H. So the pair is this, and then we have this pair also, like that. So if this is our acid, this is the conjugate base. So conjugate base. And then here we have a strong base hydroxide. This is a water is your conjugate acid. So I'm seeing a question in Discord. Let me switch over here in a second. Look at Discord. The question is, what is shifting? What I'm talking about is that if you have a reaction already in equilibria, if you add to one side or the other, the reaction will shift to compensate for it. We'll see some more of this during the practice problems that we're going to be doing. I'm just doing some acid-base review right now. Okay, so recall from last time I did mention that we do have ways to talk about acid strength. That was Ka. So this is a separate little discussion here, but I'm going to use this to kind of basically make some predictions on this problem here. So for generic acid, Ha, this is an equilibrium with its ions after it's disassociated. And the Ka expression for this is products over reactants. H plus over A minus over Ha together, like that. And then a strong acid would say that basically this side is large, meaning its value is greater than 1. And that means that the products are favored for a strong acid. Typically for a weak acid, the reactants are favored. We do have another term here. We went over negative log stuff last time with pH. It turns out we can also do that with the Kas too. So this expression is actually used more often than Ka is. So it works out where pKa is just negative log of Ka. The way this works out is that if you have a strong acid, we basically say that Ka is greater than 1. Because of the way that the math works out here, if your Ka is greater than 1, your pKa is less than 0, meaning it's negative. So you'll have a negative pKa. So if you actually look up any of the acids people are calling a strong acid, look up their pKas, they're always a negative value. You basically flip this for weak acids. So weak acids mean that they're not ionizing fully. So here the reactants dominate. So you end up with a situation where Ka is less than 1. If your Ka is less than 1, your pKa ends up being becoming positive. So pKa is greater than 0. And I just want to emphasize here for pKa, the cutoff for weak and strong is positive versus negative. So if it's less than 0, we're saying it's negative. If we're saying it's greater than 0, it's positive. All right. So if you have the Ka or the pKa of something, you can make predictions. So I actually want to let's take a look at Google real quick. So let me switch over to the browser. Yep. So right now, here I am in our my YouTube channel. We should see the stream there, but I'm just going to go ahead and Google the pKa of formic acid, which is the acid we have in that problem. So pKa of formic acid. Yep, it autofilled it. All right. Yep, there it is. pKa is 3.75. So let's go ahead and go with that. Make a little side calculation here. So for HCOOH, the pKa is equal to 3.75. And then what do you guys think? Is that a strong or weak acid that we're working with? I told you it was weak acid already, but we can confirm. The fact that pKa is greater than 0, it's positive. This is going to be a weak acid. Hope you guys are seeing that okay. I'm writing in the bottom left corner on your screens right now. This is the document camera setup. Let's just switch back over. If you wanted to calculate Ka, it's really similar to how we did the inverse log with the pH stuff. Ka is going to be 10 to the negative pKa. We saw something just like this during the pH stuff that we did yesterday. Or sorry, Monday. All right, so this one's going to be 10 to the negative 3.75. Remember, I need the negative sign added in there. And then let's calculate it. We don't leave our answers this way. We always calculate it out. So 10 to the negative 3.75. And the Ka for this acid is 1.78 times 10 to the minus 4. Okay, something I wanted to add to this discussion, make sure you write this down, and it's not in the PowerPoint. So just be clear, this is not in the PowerPoint, this next part here. We can actually predict which side dominates if you take a look at the acid on both sides. So it tends to work out where nature will favor the side that has the weaker acid. And typically the weaker, so like we're saying like we're comparing weak acid, we're comparing like this acid to this acid. Which one is stronger? Which one is weaker? And it works out that nature tends to favor the side that has the weak acid and weak base together on it. So what I'm going to go ahead and do here is just write in their pKa's and we can make a prediction. So we saw the pKa of this one was 3.75. And then the pKa of water is about 15. So these are pKa's. pKa, I think it's 15.7. Let's be exact here. I believe it's 15.7 for water. Okay, so out of the two, I'm looking for an answer in the comments. Which side of the reaction has the weaker acid? Is it the reactant side or the product side that has the weaker acid? I see one person is engaging in the chat. So the question once again is which side of this reaction has the weaker acid? Yep, product side is weaker. So remember, the lower your pKa, the stronger the acid is. The higher the pKa, the weaker the acid is. So all you do here is you just take a look at which side has the higher pKa, and if you set up this equilibrium, the product side will dominate because of the product side being a higher pKa. So here, products dominate. Like so. All right, let's go ahead and do one more acid-base problem like this, and then we can proceed. Okay. Any questions about that one before I do the next one? Yeah, if someone's talking, if you're talking in the Discord chat, I cannot hear you. All right. All right, let's go ahead and take a look at the next one. So I'm actually going to go ahead and go to the PowerPoint real quick. They're the pKa table in here. Yep, here it is. Let me load it up on the chat here. Here we go. So here we have a bunch of different Ka's for weak acids. I'm going to do conversions to pKa's to work with on these. Okay, so when you're reading these Ka's, that means that these are their acids, and if they lose a hydrogen is the reaction it's talking about. So I just want to go ahead and take a look at what if we reacted something like lactic acid with ammonia. So I'm going to go ahead and draw out lactic acid in the bottom here. Let me switch over to the view. Yep, so yeah, I upgraded my little setup today, so hopefully you guys are enjoying the new setup. So lactic acid is a, what, CH3, CHOH, and then we have a COOH. It's not really nice writing it this way. We did go over these kind of drawings. It looks like we're going to have, what, methyl group, and then a CH with an OH, and then we have our carboxylic acid group. So yeah, so there's the actual organic shorthand drawing. And I want to show you guys what is actually happening with a acid-base reaction. I don't think we're going to be doing this arrow. I'm going to be doing some arrow pushing. They call it arrow pushing here. I'm not testing you guys on it. I just want to make sure you guys are understanding what's happening with an acid-base reaction. So we do know that this is our acid. This is our base. They happen to both be weak. It's weak acid and a weak base. And we are going to have definitely an equilibrium here. Like that. And we're going to have to figure out some pKa's, but first things first, I want to go ahead and draw the product. So the thing that is the acid is going to lose an H. If you're drawing out the functional groups here, the H that you lose is this one. It's the this is the acidic H in the compound. So I'm going to go ahead and draw that without the H on it, and it becomes an O minus. Like that, and then we still have our OH here. And then if our this compound gain an H, it becomes the ammonium ion, which is NH4+. All right, so in order to finish this question here, I need the pKa of ammonium. This is one I should know. I feel kind of embarrassed that I've forgotten the pKa of ammonium, but I can just look it up. The pKa of ammonium ion is what I'm Googling right now. Ammonium ion. All right, I'm getting a pKa of 9.3. Let me show you the browser again. This is what I Googled. Yeah, I Googled pKa of ammonium ion, and then I get a bunch of different amine compounds in here. It looks like, well, no, just different organic compounds. And the pKa is 9.3. So going back to the problem here, actually I'm going to go to the file view here real quick. So before I do this, I actually need the pKa of lactic acid. We do have the Ka there. So the way to calculate the pKa would just take the negative log of that number. So it's negative log of 1.4 times 10 to the negative 4. Let me check. I think I'm thinking a question in the Discord. Let me look that up real quick. Yeah, these are examples of test questions. Someone asked, this is an example of test questions. Yes, they are. So these would definitely be fair game for a test situation. All right, so let me go ahead and calculate this. All right, so negative. Remember, you need to find the log key in your calculator. Every calculator is different. I talked about that in the last video, but it's oops. Hang on. Forgot my calculator didn't have the LOG, and then parentheses, and then that number, 1.4 times 10 to the minus 4. And then remember, we take the negative of that number, so that is going to be 3.85 for that one. All right, now we can make comparisons. pKa is 3.85, and then the pKa of this one, I believe, was 9.5 that we saw it as. So which side do you think dominates in equilibrium? The products or reactants? It's whichever side has the weaker acid. So the acids we're comparing are these ones. Out of these two, if you had to make a prediction on which acid was stronger or weaker, actually better for weaker, which acid is weaker? That helps you with the answer. It works out that products dominate here, guys. This is the weaker acid. It has a higher pKa, so this is the weaker acid. So products dominate. Products dominate. You can't. There is a way to calculate the KEQ of this reaction from these pKa's, but we're not going to go through that. I do that in OChem. We're not going to bother with it here. But I do want to just make one last little comment on this one here. So remember, your acid becomes conjugate base, so it lost an H, so acid becomes conjugate base. So I'm gonna say conjugate base, so C base for short, and then this one's gonna be C acid for short. All right. So there's your acid-base equilibrium with pKa considerations. We'll definitely do some more of these, but what I want to go ahead and do now is I want to switch over to one of the files here. Yep, so let me switch the view on the screen that you're seeing. There we go. So this is activity 3.2 that I want to take a look at. Come on, scroll. I scroll for these times. All right, so for the first three here, they're all going to be kind of the same, except for the fact that A and B are strong acids. They were on the chart of strong acids, and then if it's not on the chart of strong acids, it ends up being a weak acid. And let me pull up that chart that I'm talking about. There was a chart in the table, or the PowerPoint that I saw that we talked about last time. Yep, I am on it now, so let me pull it up. There we go. Yep, so if it's not one of these acids, it's a weak acid. If it's on this chart, it's a strong acid. So it works out where sulfuric and hydrochloric are on there, but hydrofluoric is not. Hydrofluoric has a positive pKa, where all the ones here are going to be negative pKa's. These are all your strong acids here. If it's a strong acid, it has a negative pKa. Oops. It was on the right screen. Wait, sorry, shouldn't have pressed anything. Should have just pressed that. All right, so once again, HCl and sulfuric are strong. HF is weak. The reaction with water for all of them would be the same. So what I'm going to do here is I'm going to just do a generic version. This also is in the PowerPoint. So let me switch over to presenter camera. So if you have a generic acid, HA, reacting with H2O, water is going to act as a base. Remember, water is amphoteric. It can act as an acid or a base. So this is going to be our acid. Water is going to be a base. And remember, acids lose an H, bases gain an H. Let's go ahead and show equilibrium. I do want to mention that for a weak acid, use the equilibrium arrow. For a strong acid, use a one-sided arrow. So let me add that little comment here. For strong acids, use the one-way arrow. We only typically use the equilibrium arrow for weak acids in this situation here. Anyway, what happens is we get H3O plus, and this is our conjugate acid. So that's the pair that goes with water. And then our conjugate base is A minus. So that is conjugate base. So if you're doing this with the specific examples, we could do this with HCl. So let me show HCl here. So HCl plus H2O. Let's go ahead and use a one-sided arrow here, for example. And we're going to get H3O plus and chloride. And then it works out the same too, as the pairs are kind of lining up. So this is our conjugate acid, conjugate base, acid, base. All right. Another comment I want to make here is the strongest acid that can exist in water is hydronium H3O plus. That is, oops, it's off screen. That is the hydronium ion. Hydronium. Remember, that's what you get. H plus don't just float around on their own. They will attach to water and make a hydronium ion. All right. So if we were to compare, we can see that, so what I'm saying by this here, the strongest acid that can exist in water is H2O, is H3O plus. So what I mean by that is that if you happen to put in acid that is stronger than H3O plus into water, it'll do this reaction and become hydronium. So for example here, HCl is a stronger acid than hydronium is. It will instantly react with water to become hydronium. So the pKa of this compound here is about -3. The pKa of hydronium ion is about -1.7. So remember, it'll dominate the side that has the higher of the two, the higher pKa. This is their negative values. This value is larger. So once again, here products dominate, and that proves this point here. So if any of these acids are stronger than this one, they're going to instantly become this acid. That's part of the reason why our pH scale kind of remains trapped between 0 and 14. Theoretically, we could go outside that range for pH, but typically it's normalized between 0 and 14 because water kind of equilibrates it to be within that range. So, all right. Are there any questions about what I'm talking about here with the strong acids in the water, how they become hydronium? Do you guys want me to do one more? Right. So, yes. Yeah, so the statement was because strong acids fully ionize and weak acids only partially ionize. That is correct. All right, let's go ahead and do one more of these kind of problems. So let's say we have hydrofluoric acid, so HF in water. This is going to be an equilibrium because I know that HF is not one of the strong acids, so we should have an equilibrium here, like that. And then acid, base, we're going to go ahead and show hydronium being made, H3O plus, and F minus. For the fluoride ion, conjugate base. And just like the last one, I want to go ahead and look up the pKa value for HF and see what it is. So pKa of hydrogen fluoride, or hydrofluoric acid is another word for it. I am seeing the pKa of HF as being 3.2 according to the Google. So pKa is 3.2, and then the pKa of hydronium is about -1.7. So what side dominates here? What do you guys think? What side of the reaction dominates? And I'm going to specify here we have a weak acid. People are answering. What side of the reaction has the weaker acid is the side that dominates. Reactants dominate, guys. 3.2 is larger than -1.7. Reactants dominate here. So I'm going to write that in red. All right. So this is actually very typical of, so if you think about it, if you actually look up all the pKa's of weak acids, they're all going to be higher than this value. So it works out in a weak acid equilibrium with water that the reactants dominate because these are all going to be larger than 0. So that way the side dominates. Right. So here's the comparison here. So for a strong acid reacting with water, products are going to dominate. It's a one-way arrow typically. And then for weak acids, reactants dominate. That is correct. So the question was, so acids make conjugate bases and bases make conjugate acids. That is correct. Yes. So so here is our acid. The conjugate base is this. We lost an H. And then this side, this was our base. And then we have our conjugate acid over here. All right, so I think I want to do one more acid-base problem. I want to go ahead and show you a reaction with pK is kind of the same thing. The subscript after it is typically for what you're talking about. So if you're saying pKa, you're specifically talking about acids. There's other versions of pKs out there, like there's a KSP, for example, for solubility product. We don't do in this class. But yeah, so pK just means negative log of the K value. And then the subscript after it is what you're talking about. So yeah, so once again, pKa is the negative log of the acid equilibrium constant, Ka. Alrighty, so I want to go ahead and take a look at a reaction with where water can act as an acid. So all these other ones we're using water as a base. I did mention that water is amphoteric. It can be an acid or a base. So the reaction I have here now is, what if we have water and ammonia? So ammonia is NH3. Is typically how it exists, and it's typically a gas also, but yeah, not relevant here. But it's going to work out where in this case ammonia is our base and water is an acid. And I remember the pKa for this one. I don't have to look that one up. Equilibrium. So what's going to happen here is ammonia is going to gain an H because it's acting as a base. So NH4, it's going to be a +1 now, so that's a plus sign here. And this is going to be our conjugate acid. And then with the other thing we have here, if this lost an H, this is hydroxide. All right. So what we can do here now is we can compare pKa's to figure out which side dominates. So the pKa of water, so this is the reaction where water is losing that H. It is 15.7 for water. And we looked at this one earlier to be 9.5. Which side of the equilibrium dominates? We compare the two acids in the equation, these two. Which side dominates? Yep, that's right. Reactants dominates. Yeah. All right. So another thing I mentioned it briefly earlier, but I want to make sure I formally say this to you guys. It works out where whichever side dominates, you will have the weaker acid-base pair. So both sides have an acid and base pair. Whichever side is dominating, that is the weaker pair that's together. That's typically how it works out. I'm sure there are exceptions to that, but most cases this is true. So it works out where, let me use a different color for this. I'll use blue. So this is the weaker acid plus base side. And then this side is the stronger acid plus base. So from just this problem right here, if we were making a comparison on what is the stronger base, ammonia or hydroxide, hydroxide is a stronger base because it's on this side. It's a stronger base than hydroxide. Sorry, hydroxide is a stronger base than ammonia. And then also comparing, water is a weaker acid than ammonium. I keep saying it backwards. Ammonium is a stronger acid than water because it has a lower pKa. Yeah, so the side that's weaker is together, the side that's stronger is together. Whichever side dominates, that's the weaker side. Because remember, nature prefers the weaker side. That means they're not as reactive. Nature has a tendency to flow towards the stability that you get on that side. But equilibrium here, both are reality in solution. It's all equilibria here. All right, so let's go ahead and switch back over to the work file here. I just want to kind of go through some of these here with you guys. All right, so next one here is to complete the acid and base neutralization problems. You guys should have no problems at this point doing, I'm thinking A and B should be no problem at this point. I want to go ahead and do C for you guys. So we have phosphoric acid and magnesium hydroxide reacting. So we have H3PO4 and plus MgOH2. Let's use the one-way arrow for these just for fun. Okay, so this particular acid here is can be referred to as a polyprotic or triprotic acid, meaning it can give more than one H away. So it can actually give all three of these H's away in an acid-base reaction. So this acid is referred to as being triprotic. After we do this problem, I will give you more of a formal definition of this, but for now just know that all three of these H's can be given up in an acid-base reaction. And then this one has two hydroxides available. So what we have here, we have an H plus combining with hydroxide, that is water. So it's still double displacement. And then the other part is magnesium and phosphate. Let me move my little wire, it's dangling here. So we have magnesium and phosphate. We got to be careful on the charges here. Looking at the formula for this here, if each hydrogen is a +1, that means that phosphate must have been a 3-. And we can also look at the periodic table to see that magnesium is a 2+. We can also see it here. Hydroxide is typically a -1. So if you have two of them, magnesium must have been a 2+. And then putting this together, here is our formula for magnesium phosphate. It is like that. Mg3PO42. Now we just need to do some reaction balancing. We did this earlier in the semester, like way earlier. I think it was like the first day of class almost I did reaction balancing with you guys. So yeah, this is a while ago we did this. So we're going to be balancing out H pluses, PO4 3-. We have Mg2+ to balance out, and we have hydroxide. So what I'm going to do is tally up what we have to start with, and then add coefficients to balance it. So we're starting with 3 hydrogen ions, 1 phosphate, 1 magnesium, 2 hydroxides. And then on this side, I'm going to think of this as being HOH for the sake of balancing. That is HOH. So we have 1 H+, 1 hydroxide, 3 magnesiums, 2 phosphates. So I'm just going to go ahead and start off by balancing phosphate. So phosphate, I need a 2 in front of this one. That changes my numbers a little bit. We now have 6 H's. We now have 2 phosphates. When I balance the next part here, I'm going to go ahead and balance magnesiums now. It looks like I need 3 more over here, so 3. We now have a different number of hydroxides. We now have 6 hydroxides. And then it looks like now I just need 6 of these, so put a 6 in front of water. This is balanced, like so. So there is your acid-base reaction. If you're wondering about what's what, remember the one with the H in front of the formula is the acid. The hydroxide is your base, and then if this hydroxide gained an H, this is the conjugate acid. And then here we're showing phosphoric becoming phosphate. It lost H's, so conjugate base, like so. All right, so what I mean by these these different protic acids, remember proton is for H+. So if you're saying something is polyprotic, you're basically many H's, basically what that means. So we had first our monoprotics. Our monoprotic acids are in the form of just simply HA. These can become H+ and A-. The other type I want you to be aware of is diprotic. So H2SO4, we did that one earlier, is an example, or it's in the chart that we saw earlier, is an example of a diprotic. So what happens is this can lose a hydrogen one at a time. So H2A becomes H plus and HA minus. And then HA minus can lose another hydrogen and become H plus and A2 minus. It always turns out the first one happens easiest. So I'm going to add that little comment here. Loss of first H is easiest. And what that means is that first H has a lower pKa than the others. So it turns out that if you have an acid that can have more than one H lost, typically people will list multiple pKa's. And they'll say like pKa1, pKa2, pKa3 for the order they come off. And it always works out where the first one is always the lowest because that one happens the easiest. All right, the last one I wanted to run through here is the triprotic, which was what we had with the phosphoric acid. We can have a triprotic acid. This is in the form of H3A. So you can just lose, they come off one at a time. So it's H plus and H2A minus for the first ionization. We pick up there to go to the next one. So this becomes H plus and HA, so the charge drops by 1 each time to 2 minus. And then it works out where H2 minus, sorry, HA2 minus becomes H plus and A3 minus for that one. That's monoprotic, diprotic, and triprotic. I do want to mention the example I mentioned earlier was for H2SO4. This is actually one of the diprotic acids. If you want to be technical about it, it actually has H2SO4 listed as a strong acid, but it works out only the first deprotonation is a strong acid. The second deprotonation to get this form is actually a weak acid. But yeah, splitting hairs here, we're not going to worry about that much detail. But keep in mind that some acids can lose more than one proton at a time. And here are the three types that I want you to be aware of: monoprotic, diprotic, and triprotic. All right, so switch back over to the assignment that we're looking at. Hi, we're going over acid-base chemistry, Tristan. You want to help? This next part here is having you write equilibrium expressions. You guys can do that. Which side is favored is a good one. I want to talk about number 5. Number 5 is the LeChatlier's principle question. Hi.
I'm sneaking.
Are you sneaking down? He's sneaking.
I said sinking!
Oh, sorry, he's sinking. I thought you said shrinking. All right, let's go ahead and switch over to full screen. I think I got a full screen set up here. I guess got a full screen that. And then you should see it here soon. There we go. And I'm going to zoom in. And I will move my face on this. Whoop. All right, there we go. All right, so this one here is a LeChatlier's principle question. We have a reaction turning carbon monoxide with oxygen gas to CO2 and heat. It means exothermic, giving off energy. So what the question is asking you here is, suppose that you have a closed vessel that has all the gases at equilibrium. Will the amount of carbon monoxide increase, decrease, or remain the same? So remember, carbon monoxide is on the reactant side. So if we're increasing the temperature, so I'll help you with the first one here. We are increasing the temperature. We're increasing the weight on the product side. It's going to shift to the left. So if temperature is increased, carbon monoxide will increase because we're going to increase on the reactant side. Does anybody have any questions about this first one? So once again, because heat is on the product side, by raising temperature, we're going to shift equilibrium towards the left. And then this is on the product side, or sorry, the reactant side. So we're going to increase that one. The next one here is not quite as straightforward. I forgot to mention this one here. So this one's saying the pressure is increased by adding argon. The first thing I like to do in this kind of question is check if argon is actually part of the reaction. Argon is nowhere in here. So we basically have a pressure increase. Typically what happens with the pressure increase is it'll shift to the side that has the less number of moles of gas. So this side has 3 moles of gas. This side has 2 moles of gas. It should shift to the right. So it's going to actually decrease carbon monoxide. So the second one here is a decrease. And then I want you guys to help me with the next one here. The next one here is we are adding more O2 gas. So look at the reaction first before you answer. So is adding more O2 going to decrease or increase the carbon monoxide concentration? It is going to decrease. So what happens here is we're making this side heavier. It's going to shift the other way. So we're going to end up generating more of this to compensate. So it'll be an increase in CO. So increase right here. The next one here is saying we have a chemical absorbent is added which removes carbon dioxide. Once again, check if that's part of the reaction. So we are. What do you guys think? Are we going? So it's all in reference to carbon monoxide. So would carbon monoxide increase or decrease if we're taking away some of the CO2? What do you guys think? We're going to remove CO2. Which way should the reaction shift? Yep, the answer for this one is also decrease. So by removing CO2, you're going to shift equilibrium towards the right, which you're going to remove some CO. That's going to be a decrease. The last question here is asking you about a platinum catalyst is added. We went over catalyst, we went over chemical kinetics. It turns out that catalysts do not have any effect on the equilibrium position. They just get to equilibrium faster. Remember, catalysts are all about speed. Has nothing to do with chemical equilibrium, like which side is heavier. So the platinum catalyst added is no change in the CO concentration, or the wording here says remain the same, so it would remain the same. So once again here, catalysts do not affect equilibrium position, they just make it get there faster. So no change. All right, let's go ahead and, you have any other questions about equilibrium, LeChatlier's, anything we've been going over today? We're actually almost done with the chapter, guys. I just want to do a few more little things and we'll be done for today, for this exam. All right, so let's go ahead and flip down through a couple more of these. This next one here is asking you, let me see what you guys are seeing. Yeah, so the next one here is asking you guys to write the dissociation reaction. It's basically the HA reaction it's asking for. So basically just separate them into their components. And I would just go ahead and fully pull off all 3 H's on this one. See what you get. Next ones are write the conjugate acid. Write the conjugate acid. So basically these compounds with an extra H is their conjugate acid. So it's going to be water. For this one, H2PO4 minus 1 for that one. Actually, let me just write them out here for we can have all the answers. All right, so in here, I'm writing them right here. I'm just writing out the conjugate acids for each of these. So the conjugate acid of OH minus is H2O. I'm just adding H's to them. The conjugate acid of the HPO4 2 minus is H2PO4 minus 1. The conjugate acid of the cyanide ion is HCN. And then I think water is the last one. The conjugate acid of water is H3O plus. Like that. And that's the organic chemistry circling charges. You don't have to circle your charges. It's something I do. It's an OChem thing. So. All right, similar for the next one, conjugate bases. Let's do that one real quick. make sure that you guys are all understanding what's going on with conjugate acid, conjugate base. So for conjugate bases, you just take off an H. So for the first one, H2S, you're going to have HS minus. I would also accept S2 minus. That is a diprotic acid technically. So either one is fine. I would accept. Next one there was, what is that? Sulfurous acid, H2SO3. Yep, H2SO3. So that one's going to be is HSO3 minus 1. The next one there is bicarbonate. So taking off an H would be carbonate. And then last one there is ammonia. Take off an H. We have NH3. It's now neutral. So there we go. I'll leave this one for you guys here. We can do that in office hours if you want, but you're basically identifying acid-base pairs here. Some of it's from lecture, actually. I think the second one here is from the lecture. All right. Hang on. Let me scroll. There we go. All right. Do you have any questions about anything before we do some pH problems for practice? I want to do some practice from last time for pH. Check the PowerPoint, just make sure that we're all through this stuff. Oops. File multi, wait, file full, and then that. I think we're actually done with the chapter, guys. We've gone through all this stuff. pH scale. One thing I didn't mention, I want to briefly mention here is that our bodies actually have, we need to go over buffers real quick too. So we need to do buffers first before we're done. All right, so it turns out that our body's pH is regulated at about 7.35 to 7.45, depending. You typically don't adjust your pH with your diet, so that's why I keep saying that alkaline water is BS, because your body's pH is regulated other ways. I did want to go over how buffers work, though, here in a second. I'm just making sure that we're covering everything in this chapter. Yeah, we went over pKa table for you guys. I do want to mention that the last part of this chapter goes over the acid-base. Goes over the acid-base properties of amino acids. We are going to cover that during the amino acid chapter. So for now, do not worry about this 9.7. Which goes over all the different properties of amino acids. We will cover that during the amino acid chapter, do acid base again during that chapter. So don't worry about this for now. Yeah, so isoelectric point, yeah, all this stuff here, that is basically the end of the PowerPoint, at least for 9.7. We're not going to worry about it. So I do, however, want to work on this section here. And I'm going to go ahead and make up my own problem here. Yeah, let's just do our own problem here. I'll change this one a little bit here. Okay, so it turns out that if you have a weak acid, if you have the weak acid and the conjugate base in solution, you can have a buffer situation. And what a buffer is a solution that is resistant to pH change, meaning they don't change pH readily if you add acid and base to them. So I just want let's take a look at the acetate buffer, for example. So let's go ahead and switch over here, presenter camera. So right now we're talking about buffers. These are things, once again, that resist pH change. And the reason why they resist the pH change, the main reason why, is because they will have a weak acid plus its conjugate base together in solution. Plus conjugate base in solution. Okay, so what's happening here? So I mentioned I want to use the acetate buffer as my example. So acetic acid, vinegar, HC2H3O2. We can actually show the Ka reaction for this. So here is your Ka reaction, showing it ionize. Okay, so it works out now. If you have it, if you actually have this drawn out, you can see now that if you were to add an acid to this or add a base to this, something in here is going to react with that to neutralize it. So for example, if, oops, there's only one F and if, right? My goodness. Yeah, so if acid is added. So if acid is added, we see that we have a base here. This base will react with the acid. So let's just say we have H3O plus that are acid. The base on this reaction will react with it to neutralize it. So we end up with HC2H3O2 plus H2O. So once again here, if you add an acid, you find the base in here, this is our base, that is going to react with the acid you just added. The reverse case, if base is added, the acid in here will react. So the acid here is this one right here. So we're going to go ahead and show a reaction with this, with base. So what have we added with sodium hydroxide? Is a really strong base. What ends up happening is it's going to take that H. So we end up with the conjugate base plus H2O. Okay. So once again, here's the whole thing set up. So we have our buffer situation. So once again, we have to have the weak acid and the conjugate base together. And then if we add acid, the base will react with the acid to neutralize it. No pH change. And then here, if you add a base to it, the acid reacts. No pH change. So in order to get these things to change in their pH, for example, this first one, you're going to have to add enough acid until all of this is consumed, and then pH it can change. So that gives our body a lot of leeway in pH change, because it allows our body to keep a buffer in place, and then they resist change. If our bodies did not have buffers in place, things like eating lemons would be very dangerous, because your body would not regulate the pH, and then things go out of whack if pH is out of whack in your body. So this is how. So our body uses acetates and carbonate buffers to maintain pH. The one in the PowerPoint showing the carbonate buffers, you can use that one for practice. The last thing about buffers I want to mention here is that there is an equation for this that for some reason is not in your book, but I think it's pretty important. I'm not going to do any calculations with it, but I just want to show you about it just in case you run into it later on down the road. All right, so we do know that pKa. Oh, sorry, let's do Ka. Sorry, Ka is the H plus over A minus over HA. This term is important here. It works out, though, that, let me just go get the result here, that the pH of your buffer, let me add that pH of buffer, is equal to the pKa plus the log of the ratio of the acid and its conjugate base. So I'm going to write that in here that way. So we're going to have conjugate base up top here, and then the bottom we're going to have concentration of the acid. This is called the Henderson-Hasselbalch equation. So Henderson-Hasselbalch, I think that's spelled correctly. Yep, Henderson-Hasselbalch equation. It's the equation for buffers. So if you're working in a lab where you need to make a buffer solution, typically what people will do is they will choose a weak acid that has a pKa about what they want the buffer solution to be, and then they will adjust these quantities to get the exact right value. It works out that if these two are equal, this term drops out, and then pH is equal to pKa. So I'm going to add a little comment here. So if the concentration of the conjugate base is equal to the concentration of the acid, pH is equal to pKa. Like that. And it's all because if you have the log of 1, the log of 1 is 0. And so that's what this works, and this all just drops out of the equation. All right. Are there any questions about buffers? The kind of questions I would ask about this would be maybe potentially explain what a buffer is, potentially, and also be able to draw these reactions. We saw things like this, we're just applying it now. We saw these earlier today. All right, going to give it a few seconds to see if there's any questions whatsoever. I don't know where the boy went. I think he went upstairs. You guys probably saw him easier than I did. He went upstairs probably. All right, so I want to go up. There's that. Scroll that up. All right, let's just go ahead and switch back over to the file. I wanted to work on 2 last problems, and then I'm going to go ahead and close the stream today. All right, so question here is, what is the pH and pOH of a solution with a volume of 5.4 liters that contains 15 grams of hydrochloric acid and 25 grams of nitric acid? All right, so we can definitely do this. I will talk about quizzes after this problem. So let's go ahead and do these problems first, then we'll talk about quizzes and all that fun stuff. But yeah, they're going to be soon. They're going to be soon. 8 and 9 quizzes are going to be soon. That's the short version. All right, so, oops. You guys are not seeing what I'm seeing. Let me switch over. All right, and then I want to make this fill that area. There we go. And then I'm going to zoom out, zoom out, zoom out. All right, so I want to go ahead and take a look at these last 2 here. So the first question there is, what is the pH and pOH of a solution that has that much water and then this much grams of hydrochloric acid and 25 grams of nitric acid? So the first thing we need to figure out here is, what is the hydronium concentration from these 2 acids? All right, so what I'm going to do here first is, I know we have 15 grams. Let me just write this out here, then we'll switch over to the .cam Foley. And this was HCl and then HNO3. All right, so presenter camera. All right, the first thing I need to do is figure out how many moles of H each of these is delivering, and then divide that by the volume to get a molarity for H+. Because remember, we use molarity of H+ to figure out what the pH is, and then we use pH to figure out pOH. So yeah, it's all kind of related. What I need to do first is I need to convert this to moles. So I need to know how many moles of HCl we have. And then looking at I did show you guys that app, that periodic table app. I'm going to go ahead and use it again here for my molecular weights. I need a molecular weight here. Put my phone in an airplane, because people like to text when I'm bringing my phone up here. So here is so let me back out. Come on, go back. The periodic table app I'm downloading, using is EMD, periodic table of elements. So EMD PTE. And there, over here in the options, we do have a molar mass calculator. And then I want to calculate the weight of HCl. Be careful that you use your upper and lower case correctly. And then I'm getting 36.461 for this. Okay, and then looking at the formula, we do see that there are 1 mole of H per 1 of the whole thing. So we can say that there are 1 mole of H plus per 1 mole of HCl. And then the number here would change depending on whether your acid was monoprotic, diprotic, or triprotic, right? So this is these are both monoprotic acids, thankfully. Okay, same thing for HNO3. I need the molecular weight for that. So I'm going to go ahead and use my app again. Remember, you can just use your periodic table and add these up. This is saving me time for the stream. But HNO3 is 63.013. And that is grams of HNO3 per 1 mole of nitric acid. These are both strong acids, by the way. This problem changes a little bit if these were weak acids, and we don't do that in this class. It ends up being a nasty algebra problem. You have to do a quadratic equation. Yeah, no quadratic equations in Chem 108. Anyway, this is 1 mole of H plus per 1 mole of nitric acid. And we now are ready to start calculating this problem. So let me pull up my calculator now. All right, so 15 divided by 36.461, and then that's the moles, and times 1. So for this one here, I'm going to go ahead and write we have 0.411 mole of H plus. And then the bottom part here, we have 25 divide 63.013, get that, and then times 1. So I get 0.397 mole of H plus. So in order to get the H plus of the solution, you have to get the total moles of H plus in there. So H plus concentration in molarity is going to be the total H plus, and we are going to ignore contributions from water. So if you actually, the contributions from water itself are minimal in this case. So ignore H2O contribution. Right, and then this is going to be over the total volume in liters. All right, so to figure this out, I'm going to go ahead and take our 0.411 plus 0.397, that is moles of H plus. Be an M there. Moles of H plus per volume, and the volume once again was 5.4 liter. All right, so I can calculate now. So this was 0.411 plus 0.397. I'm getting about 0.8 something, and then divide 5.4, and there we go. 0.149, I'm going to put a 150, so 0.150 molar. All right, we are not done yet. We're almost done though. The next step is to calculate pH. So pH is negative log of H plus concentration. So it is negative log of 0.150. Remember, the units drop out for pH. pH is unitless. So with that number still in my calculator, I'm going to type in the log. So alpha L, alpha O, alpha G, parenthesis, and then 0.15, close parenthesis, take the negative of that value, so it's going to be positive 0.823. 0.823. As long as you're within 0 and 14, it's okay. In a calculation like this, if you get something less than 0, I would say about 0. Remember, water normalizes to 0 and 14. So once again, if you get a pH less than 0, you want to say about 0. If you get a pH greater than 14, you want to say about 14. All right, for the last step here, we know that pH plus POH is equal to 14. So then POH is equal to 14 minus pH. So it's 14 minus 0.823. Oops. Right, and then my calculator is telling me that we have a 13.17. Let's take it to 13.18. We took it 3 decimal places. 13.176 for that one. Right. Any questions about this? Hang on, I see a question coming in, possibly. I like the quadratic equation theme. Yeah, it is a lot of information, but yeah, it would be a lot of information in lecture too. This is just how this class is. You guys know this now. So I think I'm actually going to save that last problem. And so what was the mole H plus for HNO3? So yeah, the question was, what was the mole of H plus for HNO3? I showed that up here. So this here, I was getting moles from HCl and moles of HNO3. And then did that for both of them. They are additive. So total H plus, we were ignoring H2O contribution, and then yeah, there's the rest. All right, guys, I'm going to go ahead and say this is the end of the lecture. I did want to talk a little bit about quizzes and exams, though. All right, so the quizzes, I'm thinking that they're going to be 15 multiple choice questions each. We have to do quizzes for chapters 8 and 9 still. So I'm going to go ahead and post within this week. I'm going to go ahead and post both quiz for 8 and 9. And then sometime later next week, we're going to do the exam. So I'm thinking on Monday, I'm going to do an office hour on Discord instead of lecturing. If you guys want to, I can do a stream where I just do practice problems. That's up to you guys, but we have done a practice problems between the two streams. But either way, I will be doing office hours on Monday, and I also do office hours tomorrow morning as well from 10 to 12, and it's all on Discord. Yeah, we're not going to school. We're all staying home, being safe. So yeah, so once again here, within this week, I'm going to go ahead and post chapter 8 and 9 quizzes. They're going to be multiple choice questions in Canvas. It's pretty much just bubble A, B, C, or D, same kind of thing. The short answer, the exam is going to have to be broken up into 2 assignments. The reason why we're doing, I'm going over exams right now. So the reason, hang on, so yeah, so it's looking like we're probably going to go ahead and do a Monday stream for practice problems. So yeah, just go ahead and plan for a Monday stream for practice problems. And you could wait till after that stream to do the quizzes. You will have time. They're not going to be due right away. I'm going to give you guys time. Yeah, so yeah, let's go ahead and plan on that. So instead of the office hours, let's go ahead and do a stream on Monday for practice problems. Anyway, the quizzes are going to be multiple choice in Canvas. The exams are going to be 2 different assignments. I have to break it up into 2 because I have different formats within the same exam. So you're going to have your 20 multiple choice questions for the multiple choice portion, and that's going to be a 60-point assignment because remember I gave 60 points for multiple choice. And then you're going to have a short answer portion where you have to work on paper, and that'll be the 40 points short answers. So you write it on paper. You're going to photograph with your phone. You'll grab your phone out, take a picture of it, and then upload that to Canvas. And I will post directions on how to do that. So if you've never posted a file on Canvas, I'll show you how to do it. I'm actually going to make a tutorial about it either today or tomorrow. I need it for all my classes now, so you guys all need this right now. So with that in mind, are there any questions about anything? I know it's a lot of information. Acids, acid-base chemistry, it's good times. So the question was, once we find pH, why do we want pOH? Like in what, Honestly, there really isn't all that much usefulness for POH. I think it's a conceptual thing on how this all works. So I think it's more like an activity in mental gymnastics, essentially. So it's more conceptual. POH is not all that useful. People use pH more often. But in the case where you had to figure out the hydroxide concentration for whatever reason, you know how to do it. You would get POH, and then from there you can get OH. So it's basically showing you the interconnected relationship between them. Yeah, it's more conceptual, not really all that useful in the real world. All right, guys, I'm going to go ahead and cut the stream right here. We've been on here for a while now, I think like over 90 minutes now. Let's just go ahead and cut it here, and then I'll be in Discord for a bit if you guys have questions on Discord. And then honestly, I've been leaving my computer on, so you can always ask Discord questions whenever. I may answer your question like at 11 o'clock at night whenever I happen to see it. So yep, I'll be in Discord, guys, and please stay safe. Have a good one. Stay home. You're supposed to be staying at home. Oh, speaking of staying, let me show you one more thing that I was talking about with in the Discord earlier. So yeah, I'm showing up the Discord chat right now. We were talking about this morning. Yeah, so I went to Albertsons this morning and I saw this in front of the store. Yeah, so that is not social distancing. There were like 8 people out there, kind of all grouped up, and I waited in my car until they cleared out. So that is not what you're supposed to be doing, guys. Don't do that. Please keep distance, and if you have to go out, and only go out if you have to. Don't be like the people at Albertsons this morning. I needed stuff, so I had to go. But yeah, I waited in my car for the people to walk away before I went in the store. All right, so. All right, guys. So let me see if there's any more questions about anything. Yep. Oh, wrong class. All right, guys. Have a good one. I'm just going to go ahead and cut the stream here. And I will see you guys on Monday. And feel free to ask questions on Discord or through Canvas or email. I will be around to help you guys. Hang in there, guys. We can get through this together. Have a good one.